All right, so yesterday we talked about the first derivative test and how to use the first derivative test to test for extrema. Today we're going to use the first derivative to test for what we would call concavity. And so concavity is this quality where it's concave. Okay, when we have I guess we would have a minimum on the interval, okay? So I say that it's kind of facing up, and concave down has kind of a quality of a function that looks like that. So what happens looking at concave up is the slopes between these points are increasing, okay? And so if the slopes between those points are starting to increase, the curve that represents slope is the derivative, okay? So when the derivative is increasing, the first derivative, what that means is x is concave up on that interval. What that means, like I just said, is that the slope is increasing. All right, so when prime of x, when the derivative is decreasing, the graph of f of x is concave down. If I were to graph, this is a function x cubed. Okay. It would be helpful if I graphed its derivative. Okay. The derivative of x cubed would be 3x squared. If I was graphing 3x squared, what's happening here? Well, it's decreasing. That means the slopes are steep. See, these slopes are getting less steep. And then the derivative switches to an increasing function, because what that means are the slopes of the tangent lines increasing, they're getting steeper. And so on this interval, we see if a point moves here as it goes from left to right, the slope is getting steeper. So that's what concavity looks like and how it is related to these things. Okay, so we're going to have to kind of summarize all of this in a second. At the concavity then in example 1. Is the function f of x equals x squared concave up or concave down? We might be answer that in our heads. What does that look like? Okay, well, it's caved like this. Okay. It's concave up. Concave. But what about the derivative tells us that? Well, the derivative of the function is prime of x, which equals 2x. If I were to graph the function 2x, this function, an increasing function, strictly increasing. So, since f prime of x is increasing on the entire interval, that means f of x is concave up. Okay, well, now let's take that switches concavity. Okay, now you want to think about a sine curve. Okay, sine curve, like in this area would be concave up, and this area would be concave down. Okay, and by the way, there's a point in which the concavity switches, and we call that an inflection point. An inflection point is difficult to see on the original graph, so that's another reason to use the first derivative and then eventually the second derivative. We are going to determine the concavity of 3 plus sine x on the interval 0 to 2 pi. So let's first find the derivative. Okay, and the derivative f prime of x would be, well, that's 0, the derivative of cosine of x. Okay, so let's take a look at f prime of x, which is the cosine curve, the interval 0 to 2 pi. If we were to graph this, this is a basic function, okay? Remember my little keys, I cut it in half, cut it in half again. So it goes from 1, and then it hits pi, it goes down to -1, and so on. Okay. So to determine concavity, we want to know when does f prime of x decrease and when does f prime of x increase? Well, from here to here, f is decreasing. Okay, so from 0 to pi, f prime of x is decreasing. What that means is on that same interval, f of x is concave down. All right, now this is the graph of f prime of x. F prime of x is increasing on the interval pi to 2 pi. So on the interval from pi to 2 pi, f prime of x is increasing. Therefore, or hence, therefore, f of x is concave up on that interval. Okay, so what that means is where did prime of x switch from decreasing to increasing? Well, at x equals pi. We call x equals pi an inflection point because this is where concavity changes. This is one of those things where students get sometimes confused with concavity and critical numbers. Our potential extrema, remember? There where the first derivative is 0 and or undefined, extrema unless the derivative switches signs there. So inflection points, to be an inflection point, not just where the second derivative is 0, we'll talk about that in a second, but this is where there is a sign change on the second derivative. If you think of this as the slope of this, it's going to change signs at x equals pi. If you were to look at the graph then of 3 plus sine, here I'll pull it up for you. 3 plus sine, 1, 2, 3. So it oscillates between 1 and 3. Hopefully you can see that. Concave down from 0 to pi, switches to concave up. But I got that all from the first derivative.